16 days. I mean, just imagine your core payment vendor goes completely dark for 16 consecutive days.
Right. It's a nightmare scenario.
Totally. Because in a traditional synchronous architecture, alarms are blaring everywhere, connections are timing out, and your users are seeing these massive error pages.
Yeah, it is chaotic. But at the very least, you know you're losing money.
Exactly.
Yep.
But in a modern decoupled asynchronous system, that exact same 16-day outage might just fail completely silently.
Which is terrifying.
Right. Your system could be quietly deleting thousands of your customer billing records, just dropping them into a black hole, while your monitoring dashboards show like a beautiful, comforting sea of green.
Mm-hmm. Everything looks fine on the surface.
So welcome to today's custom-tailored deep dive. We are exploring the hidden architectural dangers of background processing software and, how to prevent those silent catastrophes.
It is a phenomenal case study in system resilience today. We are dissecting a technical narrative written by Aaron Rose. It was published on the Tech-Reader blog titled The Secret Life of Python, the Backup Plan.
Yeah, it's a really great piece.
It provides a perfect lens to look at the real-world consequences of distributed architecture.
So our mission today is to uncover the mechanics of how these asynchronous systems can silently lose your most critical data during a prolonged downtime.
And crucially, how to fix it.
Right. More importantly, we're going to break down how to architect an impenetrable safety net using native AWS tools, ensuring that not a single byte of your data vanishes into the void. Okay, let's unpack this.
The source material grounds this in a very relatable scenario. We have Margaret, a seasoned senior software engineer, and Timothy, her junior colleague.
And they work in this amazing setting, right?
Yeah, they operate out of this incredibly atmospheric space, a grand Victorian library in London. The text really uses that setting to emphasize a culture of careful code craftsmanship.
I love that contrast. You have the quiet focus of an old library colliding with the high-stakes reality of modern cloud architecture.
Exactly. But that tranquility gets completely shattered when Timothy receives an urgent vendor memo.
Oh yeah, the dreaded memo.
Their external payment platform is scheduling a massive, unavoidable system migration. They are enforcing a total outage from May 1st to May 17th.
16 full days of downtime for a core dependency. I mean, in cloud infrastructure, an outage of that length is just an eternity.
It really is. It fundamentally breaks the assumptions most systems are built on.
So looking at the architecture they've mapped out in this case study, it's a pretty standard event-driven flow, right?
Yeah, they manage a billing microservice.
Okay, so whenever a transaction occurs, the system publishes a payment processed event payload to AWS EventBridge.
Right, which acts as their message broker.
And EventBridge then routes that payload to a Lambda function, and that Lambda acts as the worker. Like it reaches out over the internet to update this external payment portal.
Spot on. Now, the decoupling is great for speed, but looking at this 16-day outage...
EventBridge has to give up eventually. I mean, it cannot hold on to that event forever.
And that is the core vulnerability of decoupled systems. EventBridge is designed to deliver messages, not to act as a long-term database.
So what happens when the portal is down?
It has a built-in retry mechanism utilizing exponential backoff. If the Lambda function fails to process the event because the downstream portal is offline, EventBridge tries again immediately.
Okay.
Then it waits a fraction of a second, tries again. Then it waits a little longer and a little longer.
Right.
It will make exactly 185 retry attempts.
But those 185 attempts are bounded by a hard time limit, right? The default maximum retry window is what, only 24 hours?
Yeah, just 24 hours. And that is a hard architectural limit dictated by state management.
Meaning what, exactly?
Well, maintaining the state of millions of messages in a high-throughput broker like EventBridge requires immense memory and compute overhead across AWS's distributed servers.
Oh, sure. That makes sense.
So they cap that state at 24 hours to maintain performance. Once a message hits that 24-hour mark, or exhausts its 185 retries, EventBridge's default behavior is to simply drop the event entirely.
Wow. The memory is cleared. The billing record is permanently lost.
Poof, gone.
Thousands of events over 16 days just vanishing into the void, which honestly makes me want to push back on this entire architectural pattern.
How so?
I mean, if you are building a billing system where dropping an event literally means unrecorded revenue, why would you architect it this way? Synchronous is like a phone call.
Right. If they don't pick up, you know immediately.
Exactly. But asynchronous is like dropping a postcard in a mailbox. You just assume it gets there. If the post office burns down, no one tells you.
That's a great analogy.
So why not use a synchronous locking call? Like if we used a distributed transaction like a two-phase commit, the system wouldn't proceed unless the vendor acknowledged the payment. We wouldn't have this silent failure problem.
What's fascinating here is that the shift away from synchronous locking is actually a survival mechanism for operating at cloud scale.
Really? Survival.
Yeah. Let's look at the reality of a two-phase commit over the public internet. If you require the external vendor to lock a database row and acknowledge it before you complete the user's checkout, you are binding your application's performance directly to the vendor's latency.
Oh, I see.
If their network degrades and takes 5 seconds to respond, your users are staring at a loading spinner for 5 seconds.
And if they have a localized outage for an hour, our entire checkout flow completely halts.
Exactly.
Our database connections would pile up waiting for locks to release, and eventually our own servers crash from resource exhaustion.
You've diagnosed the exact cascade failure monolithic systems used to suffer from constantly. By moving to an asynchronous, event-driven pattern, we trade immediate transactional consistency for eventual consistency.
We decouple the systems to create resilience on the user's end.
Right. The user clicks buy, the system drops the event onto EventBridge, and instantly tells the user, great, your order is placed. The heavy lifting happens quietly in the background.
But that decoupling demands a completely different operational philosophy. Margaret points this out to Timothy in the narrative.
She does. We cannot just rely on the default retry mechanisms provided by the cloud provider.
Right, because we have to explicitly design for what happens after those mechanisms fail. We have to architect for ultimate failure. Otherwise, we are just guaranteeing data destruction. We have to invert that default behavior.
Exactly. We need a mechanism to catch the fallout when the retry window closes. Instead of letting EventBridge purge the event from memory, Margaret introduces Timothy to the Amazon SQS dead letter queue, or DLQ.
Okay, so since 16 days of downtime will definitely cause EventBridge to drop thousands of records, they need a safety net, SQS.
Yeah, SQS, the simple queue service, acts as a highly durable holding tank. But it's the configuration that makes it powerful.
Margaret opens the AWS console, right?
Yeah. Well, she uses the AWS Cloud Development Kit, the CDK, to write this infrastructure as code. She isn't just clicking around the AWS console, she is codifying a permanent safety net into their deployment pipeline.
The CDK implementation is key. She provisions a standard SQS queue and names it Payment Portal DLQ.
And then she modifies their existing EventBridge rule target. She adds a configuration block specifying this new SQS queue as the designated dead letter target.
So she is essentially rewriting the final routing logic of the message broker.
That's right.
So the mechanics of the holding tank look like this. A billing event triggers. The Lambda tries to hit the down vendor. It fails.
Right.
EventBridge goes through its exponential backoff. It hits attempt 184, waits the maximum interval, and attempts 185. It fails again.
And here is the change.
Right. This time, instead of the purge protocol initiating, EventBridge serializes the original payload, grabs the metadata, and routes it directly into the payment portal DLQ. The data is parked securely on disk.
And standard SQS queues are incredibly robust. They store data redundantly across multiple availability zones. That billing record is safe.
Awesome. But wait, let me ask a practical question here for you listening. If we're just sweeping all these failed events under the rug into a holding tank, how do we know the tank is filling up? We can't just cross our fingers and hope we check it?
You touched on a critical architectural trap. A DLQ is only a safety net if it is actively utilized as a triage center.
Otherwise, it's just a digital graveyard.
Exactly. Many engineering teams set up a dead letter queue to satisfy an architecture review and then completely ignore it. The failed messages go there to be permanently forgotten.
Which means we haven't actually solved the silent failure problem. We just moved the silence from EventBridge to SQS.
Right. But Margaret prevents the digital graveyard scenario by implementing a vital observability layer. She ties a CloudWatch alarm directly to the new dead letter queue.
Okay, so she's monitoring it.
Yeah. And she configures the alarm to monitor a very specific metric, approximate number of messages visible.
I've always found that metric name interesting. That word approximate tells us a lot about how SQS works under the hood.
It really does. It's approximate because SQS is a distributed system. The messages aren't sitting on a single server. They are spread across a fleet of nodes.
Right. Getting an absolute instantaneous count across a distributed system requires locking. which slows things down.
Yeah.
So AWS just gives us an aggregate approximation.
But for a DLQ, an approximate count is all you need. Margaret sets the alarm threshold to anything greater than 0.
Because the baseline state of a DLQ should always be empty.
Exactly. If that metric ticks up to 1, 5, or 5,000, it means an event has completely bypassed the 24-hour retry mechanism.
Oh, wow.
The moment that happens, the alarm breaches and the development team gets paged. The silent failure is brought back into the light.
You bring the fire alarm back online, but this
Uh-huh.
time the system isn't crashing. The data is just safely waiting.
And what is brilliant about this case study is that Margaret highlights another major benefit. This pattern doesn't just protect against massive, multi-day outages. It is also the primary defense against what engineers call poison pills.
Well, poison pills are a fascinating category of failure because they have nothing to do with network outages. A poison pill is just a malformed or corrupted event payload.
Right, the downstream systems are perfectly healthy, but the data itself is toxic.
Imagine a scenario where, like, a front-end bug allows a user to input a bizarre string of corrupted Unicode characters into a billing address field.
That happens all the time.
The event fires, EventBridge hands it to the Lambda, and the Lambda tries to parse the JSON. It encounters the corrupted bytes and throws an unhandled exception immediately. The code just breaks.
And if you did not have a DLQ configured, EventBridge would treat that code exception the exact same way it treats a network timeout.
Oh, no.
It would initiate the exponential backoff. It would retry that corrupted payload 185 times over the next 24 hours. The Lambda would crash 185 times.
Wow, you are burning compute cycles, incurring AWS Lambda invocation costs, and generating massive amounts of useless error logs for a message that is fundamentally impossible to process.
It is an infinite loop of failure. But with the DLQ routing configured, EventBridge eventually gives up on the poison pill and drops it into the holding tank.
So the toxic data is successfully quarantined.
Yes, the corrupted message is isolated off to the side, allowing all the other healthy billing events to continue flowing smoothly through the system.
It's like you pull the broken down car over to the shoulder of the highway so traffic can keep moving.
That's exactly it. And you now have the exact payload isolated for debugging. Engineers can look at the message in the DLQ, identify the corrupted Unicode, push a patch to the Lambda code to handle the edge case, and then process the message safely.
It completely transforms incident response.
It really does.
Which brings us back to our 16-day vendor outage. Let's look at what happens on May 18th.
Okay, the big day.
The external payment platform finally completes its migration and comes back online. Timothy and Margaret's system can communicate with the vendor again.
Right.
But they are sitting on a dead letter queue containing 16 days worth of paused billing events. We are talking about thousands of records parked in this holding tank.
A massive backlog.
Here's where it gets really interesting.
Yeah.
Because historically, the recovery phase of this incident would be an absolute operational nightmare.
Oh, absolutely. The manual recovery process was universally dreaded. Just because the data was safe in a queue didn't mean it was easy to get back into the application flow.
Think about the mechanics of manual recovery, like manually redelivering thousands of return packages one by one. An engineer would have to write a custom Python script to poll the SQS queue. They would have to read those thousands of messages in batches. They'd have to write logic to parse the SQS envelope, extract the original EventBridge payload, and then figure out how to manually invoke the Lambda function for each event.
And they'd have to build their own rate-limiting logic so they didn't accidentally overwhelm their system by blasting thousands of events at once.
And manual scripts introduce secondary risks. I mean, you are dealing with engineers who've likely been managing an incident or an outage. They are writing custom migration code under pressure.
Which is always a recipe for disaster. What if the script accidentally processes a batch of messages twice?
Right, or what if it fails halfway through and you don't know which messages were processed and which weren't? You risk duplicating payments or corrupting the database.
The operational burden was massive, but Margaret introduces Timothy to a modern mechanism that bypasses that entirely.
A native solution, right?
Yes, DLQ Redrive. This is a native capability built directly into the AWS SQS architecture.
Wait, native? So no custom scripts.
If we connect this to the bigger picture cloud providers, study these operational bottlenecks. AWS recognized that every team using an event-driven architecture faced this exact friction during recovery.
Getting the data into the safety net was automated via CDK, but getting it out required brittle custom code.
Right, so DLQ Redrive natively shifts that operational burden back to the infrastructure layer.
And it does it without requiring the engineer to write a single line of recovery logic.
Mm-hmm.
But how does it actually map the data back, though?
What do you mean?
It's not magic. There has to be a mechanism that knows where the message originally came from before it was dropped into the holding tank.
Ah, yes. It relies on metadata preservation. When EventBridge ultimately fails to deliver the message and routes it to the dead letter queue, it doesn't just send the raw JSON payload.
Okay, what else does it send?
It wraps the payload in system attributes. It preserves the exact source Amazon resource name, the ARN, of the original Lambda target.
Oh, wow. It effectively attaches a return address to the failed message.
Exactly. So the history of the event is embedded in the data parked in the queue.
That is so smart.
When an engineer navigates to the AWS console and initiates a DLQ redrive task, the SQS service reads the system attributes. It extracts the original destination ARN for every single message.
And then it just sends them back.
Yep. AWS manages the complex distributed work of asynchronously reinvoking those original targets. It automatically manages the batching, the throughput, and the network transport.
You literally click a button in the console to initiate the task, and AWS pushes the entire 16-day backlog directly back to the original Lambda function.
Just like that. The system begins processing the paused events as if they had arrived fresh that very morning.
The architecture absorbs the chaos. It elegantly turns a catastrophic data loss event into a routine, push-button operational task.
It's a game changer. Timothy actually updates his architecture diagram in the case study, realizing that their asynchronous system is no longer a fragile, silent black box.
With the DLQ and the native redrive capability, the architecture is deeply resilient. It can absorb a massive downstream failure, hold the state securely, and replay it effortlessly.
It really is a beautiful design.
So what does this all mean for you, the listener? Whether you are a software engineer building these microservices or a product manager designing the user flows that rely on them, you have to interrogate your architecture's defaults.
Absolutely.
Event-driven decoupling is incredibly powerful for user experience and system scaling, but you cannot blindly trust the built-in retry mechanisms of your cloud provider.
They will eventually drop your data to protect their own infrastructure.
You have to build the holding tank. Great system design isn't just optimizing for the happy path when data flows perfectly. It is entirely about architecting the safety nets to gracefully catch the pieces when things inevitably break down.
It requires treating failure not as an anomaly, but as a guaranteed state of your system.
Well said.
But, we should also address the complexity of recovery. We've explored the mechanical ease of clicking the DLQ redrive button to replay a 16-day backlog of events.
Yeah.
But this raises an important question, something for you to carefully consider about your own business logic.
Okay, I'm listening.
If you blindly replay 2-week-old data back into your system today, what happens if the state of the world has fundamentally changed?
Oh, wow, that introduces a whole new layer of risk. Just because the data is mechanically formatted correctly doesn't mean it is still logically valid.
Consider the business implications. What if a payment processed event from 2 weeks ago is redriven today, but the user actually called customer support and canceled their account manually during the outage?
Yikes. Does replaying that old event accidentally reactivate a canceled subscription?
Exactly. Does it overwrite a newer, more accurate database record with stale data? Does it trigger an automated welcome email to a customer who has been waiting 16 days and is already super frustrated?
It really highlights the vital concept of idempotency.
Yes.
The downstream systems must be smart enough to look at a redriven event, recognize its original timestamp, check the current state of the database, and decide if the action is still safe to perform.
Precisely. Building the infrastructure safety net, the dead letter queue, guarantees that you don't lose the data. It saves the postcard from the burning post office.
I love that.
But ensuring that the data is still valid and that your application logic can safely consume historical events when you finally press that redrive button, that is the next evolution of resilient design.
You might have saved the postcard, but when you finally deliver it, does the person even live at that address anymore?
Exactly. It is a brilliant puzzle, and it requires engineers to think beyond just infrastructure and deeply understand the business lifecycle of their data.
The silent catastrophe might be averted by a well-confined DLQ, but the logic of time marches on. Thank you for joining us on this deep dive. Keep questioning the defaults of the architecture around you. Keep looking for those silent failures, and we'll catch you on the next exploration.